Okay, we'll get back to section 11.1 here. We're talking about sequences. Let's look at some examples now where we're going to determine the convergence. There's a bunch of problems like this in the book. So what if we had the sequence given by 3 plus negative 1 to the n? Okay, if I list out a couple of terms, like if n is 1, negative 1 to the first power is negative 1, 3 minus 1 is 2. If n is 2, negative 1 squared is 1, so 3 plus 1 is 4. If n is 3, negative 1 cubed is negative 1, so 3 minus 1 is negative 2. And what's going to happen here is I'm just going to bounce between 2 and 4 each time, and so I'm not going to be approaching any one value. Because of that, I would say that the sequence diverges then. Okay. So how about part B next? What if we had the sequence, which is given by n divided by 1 plus 2n? Okay, I'm going to list out just the first couple of terms just to have an idea maybe of where the sequence might be headed towards. So if n is 1, I get 1/3. If n is 2, I get 2/5. If n is 3, 3 plus 6 is 3 divided by 1 plus 6 is 7, so 3/7. If n is 4, 4 divided by 1 plus 8 is 9, so 4/9 would be the next term, etc. Okay, now it seems like just from the first couple of terms here that maybe I'm approaching 1/2. Now I don't know that for sure. Okay, that's just a guess. So if I need to determine the convergence, which is what I'm supposed to do here, I need to show what this sequence converges to. And I wouldn't just guess 1/2. Well, let's find the limit as n approaches infinity of a sub n. A sub n is n divided by 1 plus 2n. Okay, so I got the limit as n approaches infinity of n divided by 1 plus 2n. And let's see, with that, if I multiply the top and the bottom by 1 over n, or if I were to use L'Hopital's rule, I'd still get the same answer. But I'm multiplying the top and bottom by 1 over n. I get the limit as n approaches infinity of 1 divided by 1 over n plus 2. Okay? And then I can use my limit laws and split all this up into 3 limits. Limit of a constant is always the constant. The limit as n approaches infinity of 1 over n, that's 0, right? Because the denominator is going to grow without a bound as the numerator just sits at 1. So the values are going to be, the y values are going to be getting very minuscule. So 1 divided by 2 is 1/2. And yeah, so this sequence, then, if I were to continue listing terms there, the terms are going to be approaching 1/2. Okay, so a sub n converges to 1/2, is what I'd say. In part C, we got a sub n equals n squared divided by 2 to the n minus 1. Okay. Let's see. So I'm using function notation here. Let's let, and I could list out, a couple of terms just to have an idea maybe of where it goes to. But ultimately, all these problems are going to be found by doing a limit calculation. Okay. So let's let f of x be x squared divided by 2 to the x minus 1. And we need to find the limit as x approaches infinity of x squared divided by 2 to the x minus 1. And I'm using L'Hopital's rule there because I'd be in the form infinity over infinity. And now remember, you can only use L'Hopital's rule if you're in the form 0 over 0 or plus or minus infinity over plus or minus infinity. Okay? So when I use L'Hopital's rule, take the derivative of the top divided by the derivative of the bottom. The derivative of x squared is 2x. The derivative of 2 to the x is 2 to the x times the ln of 2. Okay, and I got the limit as x approaches infinity of this guy here. Well, I'm still in indeterminate form. Okay, so I'd still be in the form infinity over infinity. And so, yeah, let me go ahead and use L'Hopital's rule again. And of course, the h above the equal sign means that I'm using L'Hopital's rule on that step. So the derivative of the top divided by the derivative of the bottom. So the derivative of 2x is 2. The derivative of 2 to the x is 2 to the x times the ln of 2. I've already got the ln of 2 there. So the ln of 2 squared times 2 to the x power. Okay, now x is approaching infinity. So what's happening here is that the denominator is going to be growing without a bound as the top just sits at 2. Well, that means that the corresponding y values are going to be getting very minuscule, okay, closer and closer to 0. So the limit as n approaches infinity of a sub n, here's a sub n, that is 0, okay, or the sequence converges to 0. So if I were to list out, a bunch of terms, I'd get closer and closer to 0, is what I'm saying there. Let's try part D here. Next. I got a sub n equals cosine of 2 divided by n. Okay, so if I let f of x be cosine of 2 over x, then calculate the limit as x approaches infinity of cosine of 2 over x. Well, let's see. So the limit as x approaches infinity of 2 over x is 0, right? Because the denominator would be growing without a bound as the top just sits at 2. So the y values are getting closer and closer to 0. Okay, so cosine of 0, that's 1, right? And that means that the limit as n approaches infinity of a sub n is also equal to 1. Okay, so the sequence here, if I were to list out a bunch of terms, I'd be getting closer and closer to 1. Okay. In part E, we have a sub n equals negative 1 to the n power divided by n. Okay, I'm going to use this rule up here, this fact about limits up here, which says that if the limit as n approaches infinity of the absolute value of a sub n is 0, then that means that the limit as n approaches infinity of a sub n is 0 also. Okay. Now I want to consider doing that whenever I have an alternating sequence. So like a negative 1 to the n or a negative 1 to the n plus 1. Those are situations where I want to at least consider using that rule there. Okay, and I'm going to use it here. So the limit as n approaches infinity of the absolute value of a sub n is the limit as n approaches infinity of the absolute value of negative 1 to the n divided by n. Now the absolute value of negative 1 to the n is always going to be 1, right? And the absolute value of n, now n is approaching infinity, right? So the denominator is already going to be a positive value. The limit as n approaches infinity of 1 over n, that's 0, because the denominator is going to grow without a bound as the top just sits at 1. So the y values are going to get closer and closer to 0 there. Okay, now because this limit gave me 0, that implies that the limit as n approaches infinity of the original sequence, negative 1 to the n divided by n, is also 0. Okay, using this statement up here. So the sequence is going to converge to 0. If I list out a bunch of terms, I'm going to get closer and closer to 0. Okay. Let's try another one here. Now, the factorial symbol, that's going to be really important for things that we're going to do in Chapter 11. Okay, we're going to do lots of things with the factorial symbol. N factorial is defined to be 1 times 2 times 3 times etc. all the way up to n. N has to be some natural number. So, excuse me, some whole number. So n could be 0, but if n is going to be a positive counting number. So like if n is 3 factorial, that's the same as 3 times 2 times 1, or 6. 4 factorial, that's the same as 4 times 3 times 2 times 1, or 4 times 3 factorial, 4 times 6 is 24. 5 factorial, that's the same as 5 times 4 times 3 times 2 times 1, or 5 times 4 factorial, 5 times 24, that'd be 120. Okay, 0 factorial is defined to be 1, not 0. Okay. Now, this formula doesn't work for when n is a negative or when n is a fraction or anything like that. Okay, so n has to be a whole number. When we take a look at this example here next, so if I have the sequence represented by b sub n, where b sub n is negative 3 to the n power divided by n factorial. Okay, well, let's see. So if I take the absolute value of this sequence, and by the way, the reason I'm using absolute value is because this alternating term here, this negative 3 to the n. Okay, so the absolute value of b sub n, that'd be 3 to the n divided by n factorial. 3 to the n, that's the same as 3 times 3 times 3 times 3, etc. Where I get, multiplying 3 by itself n times. N factorial, that's 1 times 2 times 3 times 4 times, etc., all the way up to n. Okay? And all that is greater than or equal to 0, right? Because all these are positive numbers. Now, this side is going to be less than or equal to 3 over 1 times 3 over 2 times 3 over n. Just those just those three terms there. You see, the left side is being multiplied by all these numbers that are less than 1, making the right side bigger than the left side is going to be always. Okay, so if I'm multiplying this by 3 over 4 times 3 over 5 times 3 over 6 times 3 over 7, right? Those are all numbers that are less than 1. So the left side is always going to be some number that's smaller than the right side there. 3 times 3 times 3, that's 27. And 2 times n would be in the denominator. So you got 27 divided by 2n. Okay? Now what's coming next on this is I'm going to use the squeeze theorem. Okay? Don't forget about the squeeze theorem. So the squeeze theorem is used in a couple of these problems here. Okay? And it says that, if the limit as n approaches infinity of the outer sequences are the same number, then that means that the limit as n approaches infinity of the sequence in the middle has to approach the same number as well. Okay, well, the limit as n approaches infinity of 0, that's 0. And the limit as n approaches infinity of 27 divided by 2n, that's 0, right? Because the denominator is going to grow without a bound as the numerator just sits at 27. So the y values will be getting very small, closer and closer to 0. Well, that means that the limit as n approaches infinity of the absolute value of the guy in the middle, negative 3 to the n divided by n factorial, that's 0 by the squeeze theorem. And the next thing I'm going to do is I'm using this statement here. So if the limit as n approaches infinity of the absolute value of a sub n is 0, then the limit as n approaches infinity of a sub n is 0. But by the way, it has to be 0. It can't be any other number there. Okay? So that means that the limit as n approaches infinity of the original sequence, negative 3 to the n divided by n factorial, is 0. Okay? So b sub n converges to 0. Okay? If I were to list out all infinitely many of these terms, the terms are going to get closer and closer to 0 is what I'm saying there. Okay? Now, some of these will involve the squeeze theorem. Okay? Some of them will involve this fact about limits also. Okay? just my hint with this is that whenever you have a negative 1 to the n, or in this case a negative 3 to the n, that's going to be kind of a giveaway to using that fact about limits there. Okay. In general, the factorial function and factorial grows faster than any exponential function, a sub n. So what I can know here is that because I got an n factorial in the denominator, I have a feeling that I'm going to be approaching 0, and that's exactly what happened here. Okay, and I'm using this this statement with the absolute value bars around the negative 3 to the n divided by n factorial. Okay. Okay. Why don't we go ahead and stop there in the notes, and I'll finish up this section in the next video there.